Hello, and welcome to Lecture 2 of the Preliminaries unit in Phys 1104. In this lecture, we're going to look at the process of measurements and the units that we use for talking about measurements. You've probably met the SI system, and just think how difficult it would be to do something as simple as shipping grain from one place to another if we didn't have an internationally agreed upon definition of the kilogram. In any case, the base SI units are listed here. The ones we'll deal with in this course are only these three. We'll meet the ampere in Phys 1204, and you'll deal with moles and kelvins in other courses, especially chemistry. You might never meet the candela unless you do very specific work on measuring light intensities. All measurements involve comparisons, such as comparing this pen with the markings on the ruler to come up with that the pen is 16 centimeters long. The scale on the ruler is a standard, but for this to work, somebody had to decide how long a centimeter was. This is called calibration, and it's always done using some sort of experiment. Here's an old example of a calibration method. Pause the video for a moment and read it. The important thing to notice is that it establishes a standard way of arriving at the length of a foot, and it describes an experiment that's used for calibrating it. In our modern system of units, it's important that these calibrations are experiments that can be done anywhere and get the same result. So take the definition of the second in the SI. It's a particular large number of periods of light from a transition of cesium-133. That sounds complicated, but here's basically how it works. You have light coming from cesium-133. You watch how long it takes for this large number of crests of that light to pass by some point. You time it with an unmarked clock, and then when you've gone that number of periods, you mark that off as 1 second. What I've described isn't really a practical way of doing it. The real experiment is more complicated than this, but in principle, it's the same thing. You should have met the SI prefixes in previous courses, and so at least for the more common ones, which I've listed here, you should know these already. And that's all I have to say about that. If you don't know them, learn them. There are far more than 7 types of physical quantities that can be measured, and so there have to be far more than 7 units. But all the rest of the units can be derived from the base units, using equations that express relationships between quantities. So for example, an x component of a velocity. So this has dimensions of velocity, and it's a distance along an x-axis divided by a time taken to go that distance. That distance is in meters and the time is in seconds, and so that's the units of velocity. Similarly, an acceleration is always a velocity, a change in velocity divided by a time interval. We already know velocities are in meters per second and times are in seconds, and so that gives us meters per second squared. A force can be related to a mass times an acceleration. A mass is in kilograms, and we already know an acceleration is meters per second squared, and so that gives us the units of force. Don't worry if you're unfamiliar with these equations or if you're unfamiliar with the particular ways I'm writing them. We'll get to that later. Right now, we're just interested in how we can use any equation to derive the units for a quantity. What is 3 miles plus 4 hours? Or similarly, is it true that 5 kilometers equals 5 kilograms? Well, I hope you agree that each of these are totally nonsensical. You can't add miles and hours, and you can't equate kilometers and kilograms. On the other hand, you can calculate 3 miles plus 4 kilometers, although you'd better be careful because you'll have to convert the miles to kilometers or the kilometers to miles first before you carry out the addition. The point is that miles and kilometers may be different units, but they are the same dimensions. They are both units of length. And so they're convertible to each other, and so we can add them. A dimension is just a quantity that can be measured in a particular way. So length can be measured with a ruler, time can be measured with a clock. Within any dimension, you have a choice of units, but you can only add or equate quantities that have the same dimension. there are rules that dimensions have to follow in equations. So, for example, you can't add apples and oranges, and similarly, it's meaningless to add distances and times. Similarly, it's nonsense to say apples are oranges, and similarly, the two sides of an equation have to have the same dimensions. But there's nothing wrong with dividing or multiplying different dimensions. That's how we get derived units, like meters per second for a speed. The one remaining rule to keep in mind is that constant numbers in equations tend to be dimensionless. So, for example, in the familiar equation for the area of a circle, the pi has no dimensions, and so the area is in meters squared because the r would be in meters. So, here is an equation, and I'll warn you right up front, I've made a mistake writing this equation. And it doesn't matter whether you know this equation or not, or the equation this is supposed to be, but this is one you'll meet in the one-dimensional motion unit of the course, or rather, it's a wrong version of it. And let's see that it's wrong by checking its units. So, first of all, I'll start with this side. So there's a velocity, and I've got it squared. So I know over here I've got a velocity, which is in meters per second, and that is all squared. And that equals, and again, I've got a velocity here, and that's all squared. Okay, so far so good. Meters per second all squared equals meters per second all squared. Things are looking fine at the moment. Now the rest. Okay, this 2 is dimensionless. We don't care. It has no units. It doesn't factor into our unit analysis. Now we have an acceleration. We know what an acceleration is. It's in meters per second squared. And that is all times a time in seconds. So look what we've got. We've got meters squared per second squared equals meters squared per second squared. So far, so good. Plus, and now this seconds takes out that seconds, and we've got meters per second. Oops, meters per second aren't the same as meters squared per second squared. And so this equation has to be wrong. It's absolute nonsense. It's like me saying I was 33 years old when I arrived in Cape Breton, and the time I've been here is equal to 10 degrees Celsius, and so that means my current age must be 43 moles, right? Nonsense. Absolute, total nonsense, and so is this. Let's check your understanding. As usual, if you're in the course and are doing this through Moodle, then Moodle will go on and ask you this question. Otherwise, you should still try and decide on the answer before you go on to the next part of the video lecture. So here's an equation for pressure of a stationary fluid, and I tell you what all the quantities are. There's a density, there's an acceleration g, and h is a height, and from this you can use the processes I just showed you to determine the correct units of pressure in terms of base SI units.